Hi, today I would like to present our work, Benchmarking Shortcutting Techniques for Multi-Robot Arm Motion Planning. Multi-robot manipulation could be safe, flexible, and efficient for settings such as industrial assembly. However, programming them is hard and mostly done manually with hard-coded trajectories. This has also become popular research direction recently, and the fundamental question here is how to generate high-quality motions for teams of robot arms efficiently. Among these recent works, an important component in motion planning is often shortcutting. Why is shortcutting important? We start by looking at a video comparison. On the left is RT-generated trajectories, which can be long and suboptimal. On the right is the same trajectories after post-processing with shortcutting. We see that shortcutting can significantly improve the pass quality. For multiple robot arms, shortcutting is also overlooked in literature, which we examine closely in this work. We start by looking at some background in single robot motion planning. To shortcut a single robot pass on the left, we can simply iterate over 2 points, increment them in a while loop, and see if the linear interpolation or shortcut between them is collision-free with the obstacle. If yes, we can update the original pass with a shortcut. We can also select these endpoints randomly and repeatedly check for collisions until a fixed time limit. Lastly, we can also formulate this as an optimization problem, but this often does not guarantee the result is collision-free. In practice, randomized shortcutting is often more efficient at reducing pass length. So why is this hard? For a single robot, as long as the shortcut pass is collision-free with the environment, it is a valid shortcut. However, for multi-robot, other robots become dynamic obstacles. Thus, a shortcut may create collisions with the other robot, so the timestamp trajectory must be collision-free with the other robots as well. To resolve this, we will next look at some common approaches. A simple, naive approach is composite shortcutting, where all robots are treated as one, combining all degrees of freedom. In this toy 2D example, composite shortcut can greedily apply a single shortcut for all robots at once, reducing the pass length of all robots simultaneously. Alternatively, prioritize shortcut randomly pick a single robot and treat other robots' trajectory as moving obstacles. It first select 2 configurations, reduces the timestamp of remaining trajectories, and check if the new, shorter trajectory collide with the other robot from the start of the endpoint to the end of the trajectory. If yes, the shortcut becomes valid. Another computationally cheaper technique is path shortcut. Similar to prioritized planning, it also picks one robot in 2 configurations. However, it keeps the timestamp of remaining trajectory unchanged, only checks for collision and modifies the path segment between the 2 endpoints. The trajectory can then be retimed if all robots are below speed limit. Between path and prioritized shortcutting, one method may identify valid shortcut where the other fail. We summarize the trade-off of these methods here. Since the best approach often depends on the problem instance, we present 2 multi-strategy methods to combine all 3 methods with randomized shortcutting. In each iteration, one shortcutting approach is used to select one shortcut. Round robin simply cycles through them, whereas Thompson simply adaptively selects one algorithm based on prior and result of previous iteration. We also create a dataset for evaluation. It has 6 environments with different configurations and 10,034 trajectories generated by 2 popular motion planners. Our Thompson multi-strategy method dominates all other methods throughout the anytime performance runtime curve. On average, it improves the make span of RT-generated trajectories by 25%. For CBS-generated trajectories, a state-of-the-art multi-robot planner, it also improves the performance by 14%. Our shortcutting algorithms helps real robot deployment and ensures that the robot motion is always collision-free. In summary, we analyze the problem of shortcutting in multi-robot motion planning, benchmark existing algorithms, and propose a simple multi-strategy heuristic to achieve the best performance runtime trade-off. For more information, please check out our website.